No, that was a trick. Now we're good. Even though you have the volume down.
Even Kathy's there. Hi, Kathy.
Yeah, Kathy's here. Come on up here.
Up from Florida.
Yeah. I brought the rainy weather with me.
I'm trying to get my wife on, which I thought in our tonight, but it looks like we're just getting her out of the house. That's good.
Get back in.
Nobody can, but he's supposed to do it. Yeah, I mean, we always just play best ball, you know. So whoever does the best ones, not always me.
When the ladies play, it's not even best.
Just get the ball done, but throw it, you know.
Yeah. There is no sand, there is no. Eliminated.
Yes.
I added one slide at the end of the.
Oh, did you? Okay.
Because we have this.
I call it.
So let's try ABX Mountain. Show it again.
That's my. Yeah.
And I got two other schools. I got one today, one yesterday, and one Thursday. And I've got an
I got it when you want me, that's how you every so often. You know what?
Well, one I got.
For the medical condition, it would be good.
This morning is pretty good. That's it, very good now. I had out in the stores once.
I slip that to you.
Sure. Thanks, Rick.
Yep, thanks. Overdue.
Okay, no problem.
Don't worry about it.
Yeah.
Dan Miller, like, keeping the meeting from starting again.
Throw a lather on
Like a cookie in that guy's mouth.
All right, everybody, let's get rolling. To all of us who are here in the room, thanks for braving the weather and coming out. And to everybody out there in virtual land, welcome to the ultimate meeting of our 24-25 CCAS indoor meetings, and we have a good one planned for tonight. It's said that April showers bring May flowers. And as much as I enjoy the April showers, they really have been continuing into May, and it's been a big frustration for us. And so tomorrow's solar event is going to be canceled. I'll talk a little more about what's coming up, but it's not only there's not going to be any sun tomorrow, but it's very difficult to get the rainwater out of your solar scope. Trying to observe under those conditions. We have a great meeting planned tonight. I'm really excited to hear the topic, but we also have some really good news that Bruce is going to be talking to us about the scholarship fund. And Don is going to bring us up to speed on a couple of other interesting developments that have come on. So I'm going to turn it right over to you, Don.
All right, thank you.
I've been, I think the kiss of death this year so far with regard to observing.
You like every other observing.
That being said, but I don't know. So, if we can go, can you move the slides for me or you want me to do it?
That works, huh? I'll move them for you.
All right, thank you. So first was the Cosmos, reentry. As far as I know, everyone's probably aware of this. This was basically something back in 72. This was one of the Venus probes. They renamed it after it didn't actually successfully leave the Earth orbit. And so it's been orbiting the Earth ever since. This thing was designed to land on Venus. So they expected it was going to make reentry and probably hit the ground. Right now, as far as we know, we landed in the Indian Ocean, according to the Russians. But then there's been some other measurements that said, no, not quite. So has anyone heard anything different than that?
I heard that the projections were off the eastern part of Australia or something.
That's what you heard.
Yeah,
Okay,
those are the projections from NASA and ESA. That's what they.
Indian Ocean, Eastern Australia, yeah,
Specifically.
yeah, it could be. So anyway, that's fine. It wasn't anything exciting. We were expecting it maybe to land on land, but it didn't. Thank God. All right, next slide, please. Let's see. We were expecting maybe some body blows, as I put up here, to NASA and truthfully to science in general. Part of the remit of our society is outreach, and that has many forms, I think, part of which is, of course, we lead observing sessions and we talk to people about astronomy, but we're also sort of stewards of science in general. And so I want to just bring up this topic that, you know, right now, the proposed 2026 budget impact on science is National Institute of Health, 37% reduction. NSF, 50% reduction. Department of Energy, 14 to 57% reduction in basic energy research. This is things like fusion. Okay, we're looking at the CDC of 39% reduction in budget. NASA, 20% overall budget reduction, 50% budget cut to science program. That means basically anything that's not going to the moon, essentially is going to be in trouble. And so right now, the proposal is canceling the Nancy Grace Roman Space Telescope, which is a crime against humanity. The telescope's already built. This is an incredible instrument that would have been incredible to add on to our repertoire. So that was supposed to launch either next year or the year after, but they want to cancel it. And this is on top of, remember the rover we had that they could no longer put onto the moon that was going to do the South Pole? They canceled that because of budgets. 6% reduction in astrophysics, earth science cut in half, heliophysics science cut 43%, Roger. Canceled the Mars sample return mission. This has people up in arms. That, you know, we spent billions on this whole program. So canceled Da Vinci. Remember the whole talk I gave on Venus and the lady who was running the program and they kept pushing it back. Well, now they're saying that program is dead, which was our return to Venus. So I'm just suggesting there's a lot of changes that are being proposed by the current administration that will impact, I think, science today and into the future. Future scientists need this funding to be trained. You know, many of us were scientists, and so we were trained. So I see this as a really stellar moment for us to step up. And I'm asking you to consider writing to your Congress people about this situation and making your case that they should reconsider this.
Could you, just maybe give us a few bullet points from what you just read?
I can send this out.
Send us an email. That would be,
Yep.
that way we'd have.
That would
some-
help. I can send this out to everybody.
Yeah, that would be good.
Okay.
Yeah, that would be good.
Yeah. So thanks for listening to that. It's a little different topic than what we normally talk about, but I just felt it was such a incredible moment that we're living through right now that we need to bring it up. And we are a science-based organization. Next slide, please. So let's get into what I'm supposed to be talking about. May 25 highlights really continues no sunspot days. Since 2022, the last I saw, Roger, is that about what you saw? No sunspot. We haven't had, we had zero sunspot days since
There's always
3 years ago.
Then one blew up last night, so that would have been nice to see.
Wouldn't that have been great?
But
Yeah. So as you're going to hear, the solar observing session tomorrow canceled with many of my others. Moon, we've already missed the first quarter. Full moon, the flower moon, it's also a micro moon, just means an apogee. New moon's on the 27th. Okay, so close to our hopeful observing session. Next slide, please. Planets, morning sky, you got Venus, greatest elongation on the 31st. Saturn, a rare opportunity if you can fit it in. Dave, maybe you can do it with your setup, but opportunities to view Titan's moon shadow, because Titan's in the same plane of orbit as the rings. And so it has to be aligned just right with us, and it only happens every 15 years. So this is a chance, we want to get it. So on May 15th, I calculated, check my numbers if you're gonna go out and do it, 5:49, and then May 31st at 5:09 a.m. The sun will be starting to rise, so you've got to have the planet in there and hopefully get the beginning of that before the sun comes up too much. Dave, you got a comment?
Only that Venus is nearby, but when I've been out and looking at Venus early morning, usually around 4:30 or 5 o'clock, and it's just coming up, I can barely see Saturn when
I know, it's gonna be really tough.
it's really tough. So if you have a go-to scope, it will make it a lot easier.
Evening, we still have Mars. Jupiter is gonna be fading, so you have to look in the western sky right after sunset. So if you want to see it, the better, sooner this month, the better. Next slide. I love globular clusters or globs. So M4 and M5 are two of them. The M4 is the top one here. It's actually the closest globular cluster to the Earth, about 7,000 light years away. And actually in the center of it, one of the mysteries of science has been we see stellar mass black holes, we see the supermassive black holes in our galaxy, but we couldn't find the intermediate mass black holes. So this one we think has maybe about an 8,000 stellar mass black hole in the center of it. Still to be determined. That's what the data seems to suggest. So that could be a great candidate for that. And then M5 in Serpens is basically a distant one, beautiful, as you can see there. It has what are called blue stragglers. This is a really old globular cluster. So you would expect, well, where is that new stars coming from? They're coming from collisions of stars. And so if any of you attended, was it, and this, somebody had a talk on this just recently. Roger, did you attend that one, or you probably did, Roger? Roger.
We had a speaker from Villanova from, like, what had to be 10, 15 years ago.
Talk about,
Talk about
Collisions?
stragglers, yeah.
oh, blue straggler, okay, great.
He gave us 2 presentations.
Wow.
This was ages ago. As a matter of fact, he came to our second Christmas party because there was only me and Steve Weinberg.
Okay, a wild party. Anyway, so blue straggler. So it's a fun one to look at, and just these are both really beautiful objects to take a look at. Next slide.
We've got M4 down here, where's M5?
M5 is right on top.
That
To,
here?
no, to the right, right up there.
Here?
Yep.
Okay.
Sorry, I should have pointed that out. Yeah, so right next to Antares, it's really easy to find. And then just a few hands lengths up, you'll get to M5. Okay. So what are we doing next? Well, tomorrow is not happening. So then we have our club event on the 30th, I'm hoping. And then we jump out to June 20th with Hibernia. I am going to reach back out to the park ranger who was setting up the solar observing session. See if we can maybe squeeze in a solar event. Roger, I'll work with you to see and guys to see what works. Okay. But we got Hibernia, which is great. The problem is I had Hibernia first. That's expected to be a large event with the township on the county. Friday Night Lights is one we've done for years with Natural Lands Trust. Always in July. It was in July when I started planning, and suddenly it was on the 20th of June. So I'm asking club members to focus on Hibernia. Don here is going to focus on Friday Night Lights with a small handful of people, just so we have representation there.
But if it's gonna be a good night, there's always plenty of scopes at Friday night.
Yeah,
More than
enough.
where we're gonna need the manpower and everything.
Yeah, so please, I ask you, focus on this. If you're really interested in Friday Night Lights, talk to Don, see how many people have signed up for that, but please focus on Hibernia, okay?
Hey, Don,
Yes,
you've listed a rain date for the event tomorrow on 15th. Is that hypothetical or is that really gonna be the rain date? May 15th?
that's not the rain date.
Okay.
Go ahead.
I just want to mention a couple things. So I sent an email out a month ago. One of our members, Bob Borowski, donated this 8-inch lead, which originally was on a fork mount, but it had deforked, as they say, by Sky Limited. And it's on an advanced VX mount, an AVX mount from Celestron. This is all the stuff that goes with it. There's even a Revolution Imager. That's like a $300 eyepiece, computerized eyepiece, video camera. So there's all this kind of stuff. No one expressed any interest. I just want to show it again. This is sitting there in our basement and no one's using it, and it should be getting some photons. So I'll send another email out. I just got 2 more telescopes within the last week that are very small. They're probably giveaways. This will be a lending scope. So if anyone wants, this is like $2,000 worth of equipment. It's amazing stuff. So if anyone wants to push the envelope and learn a little bit more, it's not a beginner scope, but it is a very nice bit of equipment. So I just want to show that. Sorry?
How heavy is that?
Not crazy heavy. I mean, the meat itself is probably only 5 or 10 pounds. The mount is a little more, maybe 20, but it's not terribly heavy. And it's just all this stuff that goes with it. It's amazing.
No counterweights?
Well, there's the counterweight that hangs off here is probably 10, 15 pounds on its own. So,
Is it a go-to?
it is a go-to. Oh, yeah.
It's an equatorial.
It's an equatorial mount. So you have to, when you set up, you have to crawl down behind it and look through the pole. It has a polar scope. You can look through the polar scope to line it up with Polaris. So anyway, it's great equipment. I'll send another reminder out, but so far no one has expressed interest in it. So it's new. And one other thing, while Sadvi is here, I want to make sure everyone knows that Sadvi Prasad has won 3rd place in the Horkheimer Journalism Award for the astronomical reading. I think you already have a long sleeve small t-shirt, right? Well, in honor of you, now you have a short sleeve one. So let me get this. And actually, Dave, why don't you present this? We'll get a picture. Barb, can you take a picture? So yeah, this is the big deal. 3rd place in the national competition. This is a big deal. And then you get an outreach pin from the Night Sky Network.
Can we get a copy of what you wrote?
Yeah, what we need to do is we need to have a picture of Sadvi and her essay sent to John Hepler for the newsletter.
Yeah, if we could do that, that would be great.
Mhm.
Got it? All right, congratulations.
Well,
And while
I'm happy to announce
Things
that I was a sponsor. I'm happy to announce that.
and while we're at it, the Kathy can come forward. Again. 2 years.
Just a small roast.
And here, Dave.
Because you're never around. But the Night Sky Network has been awarding you this stuff for the last 2 years. Please take your pins to the doctor and have to leave them. It's nice to get.
Hi, Bruce, I see Julian has joined.
Yeah, just one brief announcement.
Yeah.
So, I think everyone knows, we have a scholarship fund, right? 3 $1,500 scholarships that we award to Westchester University students that are either in earth science, geoscience, minoring in astronomy, physics, computer science, that express, career interest in astronomy, planetary science, space-related fields. And so, because of your generosity, we raise the money to support these 3 scholarships. We have Mark Gagne in the Department of Earth Sciences, who leads a committee that reviews applicants so that it's done very objectively on the basis of merits primarily, and also need to award these scholarships. So this year, there were 12 applicants that made the cut, and the 3 recipients have been selected. And I just want to mention who they are, give you a brief blurb. But in the June issue of Observation, we'll actually have a little bio on each of them, photograph what some of their interests are, their hobbies, even their career interests. So one award went to Kate Fredericks, who is a junior geoscience major and astronomy minor. She's working on the Dark Skies project within the university, and she's interested or planning a PhD program in planetary geology. So definitely a good fit. Second individual was Ella Ashman. She gives a lot of the planetarium talks for the department in the Mather Planetarium, and she's also a geoscience major. And the third recipient is Cecilia Bates, who is a physics major, an astronomy minor, and an active member of the astronomy club. So 3 really worthy students, again, made possible because of your generosity. So thank you.
Oh, before I forget, 2 years ago, Abney got the same award that Sagu got this year.
Yeah.
Yep. So that's really good for our club. It shows we have a lot of active young members, and that's critical to our club to survive. So thank you, young people.
Introduce you.
I think so.
So tonight's speaker, really excited to introduce Dr. Julian Witt from MIT, DeWitt. And all of our speakers are impressive. This guy, if you go to his website, it says his primary interest and expertise lies in the field of data science, where math and science are brought together to make sense of newly accessible pieces of reality. Okay? However, digging deeper, it's really impressive in that about 8 years ago, Julian was part of an international team that actually was instrumental in the discovery of the TRAPPIST system, which I think we all know, the 7 rocky planets that orbit TRAPPIST-1. And he actually spearheaded a lot of the initial studies evaluating the atmosphere of these exoplanets with Hubble, and then with a number of ground-based telescopes as well. Beyond that, he developed and applied new analysis techniques to map the atmospheres of exoplanets, to study the radiative and tidal properties of exoplanet-star interactions, and to constrain the atmospheric properties and mass of these exoplanets from spectroscopy data. He's also done a lot of work studying the main belt asteroids and our understanding of meteorites, and also with regard to planetary defense capability. So a really impressive resume for a relatively young guy. In terms of his background, he joined the Earth, Atmospheric, and Planetary Science faculty at MIT in 2018. He's a member of the Disruptive Planets group. He has a bachelor's degree in physics and mechanics and master's in aerospace engineering from the University of Liège in Belgium, completed master's studies in astrophysics, planetology, and space sciences, and then moved to MIT to get his PhD in planetary science and pursue postdoctoral studies. So tonight, his talk is entitled "Searching for Extrasolar Life While Defending Earth-Based Life." So it's a real privilege to introduce Dr. DeWitt. Thank you.
Hi, good evening, and thank you for having me. Can you hear me well?
Yes,
Can I get a thumbs up in the attendance? Okay, great. So today, I was thinking that we'll do something that is really not usual, and we leave space for question as we go. How does that sound? Is it something that's is it a format that would work for you and your audience?
Sure.
Yeah, okay, great. It's just so we make it dynamic, right? I mean, it's the end of the day, and if I just go for 40, 45 minutes, I'm sure it's not going to be the same in terms of engagement as if we leave room for back and forth. So that sounds good to everyone? Perfect. All right, so let me share my screen and we'll get going. Can you see this well?
Yes.
Yeah.
Okay, brilliant. So yeah, as you said, I'm a faculty here at MIT, and I started the group, Disruptive Planet Groups, for a reason that you'll see in a second. And it's a talk that goes in different direction. I understand you have a scientifically savvy audience, so I want to touch upon a few things and then see where you'd like to ask questions and dive into some of the details. I'll skip most of the details to make sure that we don't get bugged into these, but if you're interested in learning more, stop me and we go for it, or we can go for some more detail at the end of the talk. All right, so I want to make sure that despite the fact that you're a scientifically savvy audience, I provide the right level of introduction to the talk I'll be giving. So I will start by talking about why do we care about worlds that are so far away? Why do we care about exoplanets, right? Then I'll provide a tiny bit of history with what has happened in this young field, that is the field of exoplanetary science, and I'll talk about how we detect and study these exoplanets. And once I've done that, I'll talk about who we are, so what my group is doing and what we do, so it will provide the credential basically for some of the ongoing discussion or the discussion that we'll dive into right after. After that, I'll dive into 2 specific concerns that we're addressing. So that's one of the portfolio project that we have in the group that relate to the fact that we've moved into an era of high information content with the new generation of telescopes. And now we are limited by the models that we have to make sense of those pieces of reality, as you described in the bio, because really most of what we do relates to data science. But in order to translate that information into scientific inferences in a reliable manner, we need to upgrade some key models, and I explain that further. Once we've done that, I'll finally be able to talk about moving towards searching for exohabitats, so habitats beyond Earth, specifically around other planets, not just in our own solar system. Even so, that's happening here too, and if you'd like, we can talk about Mars and Venus, amongst others. And once I've done that, I'll talk about planetary defense, but I'll keep that part for the later bit, so there'll be a bit of suspense with regard to what do I mean about planetary defense when I talk about extrasolar systems. All right, so why do we care about worlds so far away? Let me just minimize that so you get to see my whole screen. Well, the reason is pretty simple. You may think that we've learned a lot about that one sample that is the solar system. You know, we have these planets that we get to send spacecraft to, something that we'll probably not do in our lifetime for extrasolar system. But despite the amount of information we've been able to gather about this one, it is still one unique sample, right? And so the analogy I like to make for students that are not necessarily from scientific background is that the extent to which you'll be able to predict, say, the outcome of a political election would be somewhat okay if you were to survey different people, but if these different people, say 5, 9, 10 of them are from a same family, it's pretty likely they're going to be sharing the same history and values, and so you'll be biased in your understanding and your capability to predict what's going on there. Same thing with the solar system. We have 9 or 8, depending on your age, planets in this system that have formed at about the same time around the same type of star, and they have evolved together. So naturally, there is only so much we can learn about planetary formation, planetary evolution, and so forth. And so when we move towards other planetary systems, we find things that were unexpected. One easy example to talk about right away is, I'm sure you've heard about hot Jupiters, these planets that are gas giants that we are expected to form or see form beyond the ice line, say 5 AU for a sun-like star, to be able to gather enough mass to become that big. But for the first few detection, in fact, for most of the gas giant planets we found them forming, or not forming, but we found them much closer to the star with orbital period of just a few days instead of 11 years like Jupiter. We've also found planet without star, literally free floating through the galaxy. Planet with multiple stars like Kepler-16 that offers iconic double sunset like Tatooine in Star Wars. In fact, as we speak, the record for stars in the sky is 4. One planet is in a system with 4 stars. We find planets with incredible ring systems, such as J1407b that you see on the left. I mean, so obviously, all of these are artistic rendering. I'm not going to say that every time. Everything we see for exoplanet is one bright dot. So whatever I'm showing you, these are artistic rendering. Okay. This being said, some of these, like this one, has incredible ring system, 37 rings, about 200 times larger than Saturn rings, so big that if Saturn had such ring in the sky, it would be bigger and brighter than the moon. And this is what it would look like. We found planet literally dying as we speak around that star, being pulled apart by the strong differential in gravitational field. Right? So that already in a few minutes give you a pretty good understanding of why it matters to start going beyond the solar system, because you can find things that were unexpected and it helps you disrupt your understanding of these processes, hence the name of the group. And so a bit of history. I don't want to say, I won't say that everything started with the discovery of 51 Peg B, because initiative that aimed at discovering planets around the star started, way back. These were ideas contemplated thousands of years ago, but the technology really started flourishing in the 80s. And by 95, we had the detection of the first exoplanet around a main sequence star, 51 Peg B. And that led to the Nobel Prize in 2019 with colleague and friend Didier Queloz and Michel Mayer, Swiss, for that discovery of an exoplanet around a main sequence star. And if you plot this planet in terms of size versus orbital period versus the planet in the solar system, which you see in red, you can appreciate, and that's in log space, how different it is from what we had in the solar system, right? It's a gas giant that is orbiting its star much, much faster than Jupiter and Saturn orbit our own sun. And so it is the one that led to the Nobel Prize, despite the fact that before a few other objects were known. I'm not going to get into the details of what that happened, but long story short, either they were found around a pulsar or they were too close to the planet brown dwarf boundaries. And in any case, 51 Peg B was the one that clearly was an exoplanet around a main sequence star. So it was coined as the first exoplanet in 1995. I'm going to move forward to give you a sense of where we're at right now. At some point, we find the first planet for which we could get a size estimate, and I'll get to that in a second. You can see that we're first able to find massive planets, and I'll get to that in a second too. And then progressively, we move towards smaller and smaller planets. And most of them, we get constrained on the size. That's why they're appearing on the right panel. Okay? And then you can already see two big trends. These numbers are slightly outdated because it's probably a slide that I'm not updating every year. But the bulk of the idea is there. With these detection, we managed for the first time to place constraint on the Milky Way population, right? We can't detect planet in our neighborhood of the galaxy, but then we can expand and use this number to extrapolate on what's happening in the whole galaxy. Interestingly enough, formation model help us appreciate the fact that there might be as many times as 10 times the number of planets around stars than there are free floating, because they get to expulse a large fraction of these embryos during the formation process. But also, and most importantly, we directly see two different planet time. I'm going to highlight them in color. In red, you have the hot Jupiters, these gas giants close to their star. And in gray, you have these super Earth, which are now actually mini Neptune and super Earth. These are planets with no analog in the solar system too, because they are filling the gap in the size distribution between the largest rocky planet, Venus, and the Earth, and the smallest gas giant, in fact, ice giant, so Uranus and Neptune. Can you confirm that you see my mouse when I move it around? So
Yes.
you do? Perfect. Excellent.
Hey,
Then we can
George,
keep on. Yes.
So the techniques currently used for detection, don't they put an inherent bias on what you're looking at since they really don't see very small objects?
They do. Thank you for asking. And I'll get to that in a second. But you can see here, you see this line, right? Almost. You have a detection bias or an observational bias that relate to the orbital period and the size of the planet. Why? Because if you stare at the field, most of these detection here are from Kepler. We have some more of tests that have been piling up a bit further down. But long story short, if you stare at a field and you're looking in this case for transit, so when the planet passes in front of the star, that star, which is really just one PSF, so all of the flux from the system is condensed in one bright dot. I'll get to that in a second. Drops, right? If you have a big bright star with a big planet, you can detect that transit in one go. If you have a shallower transit, you need to accumulate many transits to be able to build the signal to noise ratio needed for that detection. So small planets needs to be on a short orbital period in order for a same baseline, say 1,000 hour on target, to be able to accumulate enough transits to lead to that detection. And that's where you have this relationship between how small a planet can be and how far away it can be from its star to still allow for the detection over a given period of time. Basically, for the smaller the planet, the more transit you need to pile up to build up that significance of your signal. And that's why you cannot go super far and detect these small planets. Does that make sense?
Yeah.
Brilliant. Okay, so finding these new planet type helped us, challenge our understanding of how they form. So for example, for hot Jupiter, we had this understanding that gas giants form beyond the ice line, and then it leads to the question, well, okay, how do we get to this? And so maybe they actually form in situ, they actually form right away next to their star, which really is still challenging to explain, but there are mechanisms that could lead to that. Or there are various phenomena that leads to some form of eccentricity excitation and then a tidal migration. And I won't get into the details, but that is really what it allows us to do. Find things that were just not expected by our model and then challenge our models. And similarly for the Super Earth, we actually realized not so long ago in 2017 that this blob was actually two separate blobs, one that we would call mini Neptune, a radius valley, and then on the other end of that, super Earth. So the current understanding is that these form with primordial hydrogen-dominated atmosphere, and then some of them get to very quickly lose that hydrogen-dominated atmosphere, and they end up with a higher mean molecular weight atmosphere, and they are called super Earth. So this is an in-between because the transition is relatively fast on geological timescale. You don't find many of these objects because they transition very quickly from one state to the other state through atmospheric escape. And you can really see this depletion of objects between 1.5 and about 2 Earth size on this histogram. There is a 1D version of this 2D histogram. Okay, so that's really helped us highlight planetary type that we just don't have in the solar system, right? As a reminder, we have Earth-sized planets, and then we have ice and gas giants, but we don't have mini Neptune or super Earth in the solar system, unless, of course, Planet 9 actually exists, and we would have that super Earth of a few pixels. All right, here, this is Spitzer data for the exoplanetary system HG 189733 that has 2 stars, so A, B is the planet. And so the question is, how do we get to study a whole planetary system from a bright dot? And it goes back to data science, hence, making piece of reality, just getting these bits of information and trying to make sense of them. And that bright dot has a flux that's changed over wavelengths or color and over time. And so we can leverage these two things to do either radial velocity, which I'm pretty sure you're all familiar with. So we can use the Doppler effect on the stellar spectrum that may be shifted to the red and then to the blue to derive the period associated with the companion, be it a planet or another star, and its mass based on the amplitude. And then the technique I was just talking about, the transit technique, from which we can derive the planet size from the flux drop, which relate to the planet to star area ratio. And the period between 2 dips lead to the orbital period as well. Great. Then for the few, back in early 2000, a few of these planets were detectable by Bose technique. So for them, we could start talking about the density because we had the bulk density, which lead to discussions about their bulk composition, which can nicely be seen on this plot that shows a handful of exoplanets. Forget their color. The color is really just related to the estimated equilibrium temperature. We don't need to talk about that right now. But they are plotted as a function of their size and masses versus what you see here in different colors. These are isocompositional curve. So the one in red is easy to understand. It is the size that a planet would have for different masses if it was pure iron, right? So planets that are falling close to that line are so dense that they are almost entirely composed of iron. And on the other end of the spectrum, interest of size-mass relationship, if something has a mass of 1 Earth, but happens to be about 2.5 Earth radius, then it is something that is mostly a small version of a gas giant, basically. So primarily composed of hydrogen and helium, okay? And then you have everything in between. So that's what we could be doing in the early 2000s. That's a bit later once we start getting Kepler planets. Then there's more to say about the distribution of object with mass in the Earth to 10 Earth mass regime. And we can really look at this transition between rocky world and at around 4 Earth masses world that are actually able to hold on to a thicker atmosphere, an atmosphere that most likely is still primarily rich in hydrogen. So that's what this plot really highlights here, a transition in these mini-Neptune type of regime. Great. So that's about the bulk density. Once we get the mass, we get the size, we can get to bulk density. But the thing that's really excited to me is when we start leveraging spectroscopy. And spectroscopy can be done, and was done first for exoplanets, by leveraging the transit configuration. When a planet passes in front of its star, a small fraction of the stellar light is going to go through the atmosphere and is going to be filtered by the atmosphere. In other words, the Sorry, my English brain is starting to fade by the end of the day. So that's what's happening. In other words, what's happening is you do have some information about the atmosphere that is imprinted on the stellar spectrum for the small annulus that relate to the atmospheric area. Okay, so if you want to think about it in two wavelengths, one that is highly absorptive, the other one that isn't. At the wavelengths where the atmosphere contributes significantly, you're going to have a planet that appears slightly bigger because the atmosphere will also block the stellar light, and so your transit depth is going to be slightly deeper, right? So one of the first spectrum obtained here with Hubble and the instrument WFC3 is the spectrum of the hot Jupiter AG 209458b, where you can see that the planet appears to be bigger, about 1% bigger at 1.4 micron. And that is due to the fact that you actually have water vapor in the atmosphere of that planet that is also contributed to the transit depths. And that's why the transit depth is slightly deeper. Okay. All right. So that's a quick overview of what has happened between, say, 1995 and 2010, 15. So now what about us and who are we and what do we do? Well, the group that I lead, as I said, is called the Disruptive Planet Group, and now you understand why. And our goal is to discover and study, that's our mission statement, discover and study new world in order to consolidate our understanding of planets and habitats. And for that, we have a portfolio of projects that falls into three big categories, and I quickly just provide an overview of them. The first one relates to discovering new worlds, and for that, we've, as you said, contributed to the discovery, amongst other things, of the TRAPPIST-1 system, 7 Earth-sized planets that are found around a star that's small enough to actually allow for the characterization of terrestrial world. It is still today the best place to characterize Earth-sized world and search for signs of life, and we will get to that. That was found by a prototype telescope called TRAPPIST, 60 centimeter. Since then, we moved to the parent project that also has a Belgian name, the Speculoos project, Speculoos being Belgian cookies, TRAPPIST being Belgian beers. And so we have a network of now 6 1-meter telescopes spread between Chile and Tenerife in the Canary Island. This is Artemis for Tenerife and in Mexico. So this is some of the senior scientists that have worked on the project with me. And what we aim at doing with this project is to find high-value planets. And there are two big categories of high-value planet. I'm going to showcase that. On the one hand, we have Earth-sized world that are temperate, but are also with an expected transit signal, so variation between wavelength that would make them characterizable, somewhat close to TRAPPIST-1, because as I said, TRAPPIST-1 is still the best system. And so this planet that has been coined by Earth when it was published is actually right in this regime. And we can get into the details. If you have questions, please do ask. And then on the other end of the spectrum for high-value planets are planets like this one, which was called the cotton candy planet, simply because it is a big planet with an extremely low density, puffy, which means if you think about the information imprinted by a very large atmospheric annulus, there's a lot that we can do with spectroscopy, all right? And when I say it's very, very low density, this thing is 20 times less dense than Jupiter, right? This is how low density we're talking about. It's literally the same density as cotton candy. And so when you have such world, you can expect insanely precise transmission spectrum. If you remember what I showed you with Hubble, that was this tiny corner of the plot with huge error bar. This is one transmission spectrum of JWST, and you can see beautiful features of CO2, water, methane, and so forth. And so you can get exquisite constraint, not only on the abundance of this gas, but also you can map out the whole temperature pressure profile of such a world. So that's what I mean by high value system for which we can really do in-depth characterizations. Right, so I'm going to skip characterize for a second just to give you a sense of what we do when we contextualize, meaning we get enough information about one system to improve our understanding of physics, or we've studied enough worlds to start connecting the dot, and it's the population-based information that comes to challenge or improve our understanding of fundamental physical processes. And basically, that's where we do the science. Yep.
How do you get the temperature, how do you get the pressure temperature profile with altitude on one of these planets?
Yeah, great question. So interestingly enough, the very first work that I did in the field of planetary science. So I'm an engineer by training, and then I moved to planetary science. So I came with a mathematical background, and the first piece of work that I did is derive the mathematical equation behind the information in the spectrum. And what you can see, and I'll get to a slide that showcases that briefly. We won't get into the derivation. What you can see is that there is as you record this, for example, feature of CO2, there's information about the broadening of hundreds, in fact, hundreds of thousands of lines of CO2 creating this feature, and each of these lines are recording information at different pressure or altitude level, and each of them have information about the temperature as well. And so you have information about the abundance of CO2 as well due to the shape of the feature here and then the shape of water and so forth. You also have information about your temperature and pressure profile in this spectrum. That's a high level explanation. But that's what's happening. Fortunately, we're probing, if you look at the transit depths here, that's probing and you have the scale height, right? So you have an idea of how many how many orders of magnitude in pressure or range of pressure you're probing over such a spectrum. Okay. So that's how you get information about 3 or 4 orders of magnitude in pressure, or the equivalent of 8 scale height in atmospheric depths. Okay. So to contextualize, what I started to do for my PhD next to what I was just describing is creating maps of exoplanets. And we won't talk too much about this, but I think it's important to highlight what can be done despite the fact that we really only see one bright dot on our detectors. When a planet passes behind its star, it's scanned in 2 different directions. And so if you do a careful monitoring of the flux drop during the occultation and then the egress when the flux come back up, you can actually start recreating maps of world. And so in 2012, we did the first 2D maps, and now we're getting at a place when we can do 3D maps. But already then, what we could do is start creating maps of worlds here, not in the infrared, but in the visible, and show non-uniform cloud distribution, for example. And showing a non-uniform cloud distribution for this world, which is Kepler 7b, allowed us to discuss the composition of these clouds because we knew the temperature of the day side. We could constrain the temperature of the night side with basic GCMs and get a sense of what are the type of cloud particle that could condensate on the night side and lead to this permanent half day side cloud coverage, mostly clouds made of magnesium and silicates. And that is really my favorite. We have, and that's something that, in astronomy, we're very passive in terms of observer. So it's very difficult to try and come up with hypotheses like you could in biology and chemistry. You can come up, try something in the lab, and then see what happens. And one of the things that is quite exciting to do is imagine taking a planet and dumping a huge amount of energy and see how the energy is redistributed. Well, in some cases, which is what you see here, sorry, it's a bit small, but that'll make the point. We do have this exoplanet HG186, HG80606b, which is on a highly eccentric orbit. It has a period of 111 days and an eccentricity of 0.93, which means it goes as far out as Mars, but then when it comes close by to its star, it passes 6 stellar radius away from its star. And over the course of 12 hours, it changed in temperature from 400K to above 2000K, and then it cools down. So you get to dump every 111 days, or more than 1,000 times the Lewis-Schumacher impact in Jupiter. And you get to see what's happening to this world. So you get to see the radiative and convective processes in the atmosphere of this world, which really is important. You're basically looking at the tidal response, at the impulse response of an exoplanetary atmosphere every 111 days, which is key to understand processes that are inaccessible for planets in steady states on circular orbits. So this is the kind of thing that we can do, and that's where really some cool science come in. So one last process that might be of interest to you. On Valentine's Day 2017, we published a study where we revealed for the first time stellar pulsations or stellar heartbeat induced by a planet in the form of very, very small pulsation detected in Spitzer data, which were validated recently by the Hubble Space Telescope. And these harmonics, we recently explained them, and through their detection and the whole new framework to explain these planet-star transient tidal interaction, because as the star evolves, it has different mode that can synchronize with the eccentric orbit of the planet, and the planet can serve this mode. And despite what the field was thinking for decades, gas giants happen to not migrate monotonically, meaning that they progressively and slowly lose eccentricity. What we show is we show that they go through basically surfing various modes. Sometimes they very quickly lose eccentricity, sometimes they gain eccentricity and change inclination depending on the mode they serve. And so it's a very chaotic, somewhat chaotic process depending on the mode that they're picking up on. So it really completely changed our understanding of hot Jupiter formation and obviously evolution. And that's really what's happening in contextualize. All right, so that's for the kind of thing that we do, and hopefully that will seed or help support questions. And now the bulk of what I'm going to talk about before we talk about habitats relate to what we do in Characterize. And really what we do in Characterize aim at enabling the next era of high precision measurements. Why? Well, what's been new is the fact that we have access now to exquisite facilities like the James Webb Space Telescope, but we have the ELTs coming in too, which means we have extremely precise data with much higher spectral resolution. I know I write high, but it depends what field you're coming from. I mean, 1,000 in spectral resolution is pretty good when you used to work with Hubble, but obviously we have hundreds of thousands with a radial velocity instrument, but for different types of science. So it's high in the context I'm talking about. And we have much broader spectral coverage. So the information content has significantly increased. To put that into perspective, what you see here is transit depth versus wavelength. So it's getting back to this CO2 feature that I was just talking about for WASP 193. And this is the first detection of CO2 in an exoplanet atmosphere. And I'm going to put this next to all of the information we had about that planet before. That's the same planet. You have the WFC3 wavelength range I was showing just before for the first exoplanet survey. You have a bunch of other Hubble data points. And then you have here the two Spitzer photometric points at 3.6 and 4.5 micron. And this is what JWST added to it. You can appreciate the sampling. So we are actually able to map out these features, and that goes back to what I was talking about before. If we can sample these molecular features, we can start constraining the temperature profile, the pressure profile, the abundance profile, and so forth. And that's just an example, right? The actual spectral coverage of JWST goes all the way out to 0.6 micron. So much more precise, better sampling. And so we are really moving into an era of decryption where we can make strong or get to strong inferences with regard to what's going on in exoplanet, not just identify molecular feature, which is, I don't want to say that was the bulk of what we were doing before, but we can really do much, much more right now. So what are the bottlenecks? Like, what really is happening in the field to get to that? Well, what is behind the transmission spectrum relates to the instruments that has been upgraded, and then all of the other things. The star is this thing that emits the photon that are going through the planetary atmosphere, how light and matter interact relate to the opacity models, and then the photons are coming to the instrument. So this is doing much, much better. But if we want to do analysis, we need to have a really good modeling or understanding of each of these other blocks. And these things do need upgrade. So I'm going to just talk about two things during this talk. I'm going to give a bit more information about our opacity models. So again, how much we know about light matter interaction, because the information about the atmosphere is imprinted or encoded, if you'd like, on the stellar spectrum or the stellar lights through that process of light matter interaction, right? So we need to understand how it works to be able to decode the spectral information and retrieve the information about what was going on in the atmosphere when the light interacted with the material there. So I'm going to start with that. And that's the opacity challenge for which we've provided a solution. So getting back to the question you had before on, what can be constrained with regard to planetary atmosphere, the first bit of work that I put out, I guess the second one, but there was the two big part of my thesis at the time, related to understanding what is the true information content of a transmission spectrum, which is what you have here. And what you see in the different boxes are the posterior probability distribution of parameters that can be inferred from a synthetic transmission spectrum. And we don't need to go into the details unless you want to know more at this stage. But long story short, I'm going to just skip the math to get to one piece. The apparent size of the planet is encoded in a series of integrals that are basically related to the number density profile of different molecules weighted by the cross-section, which is your opacity model that says how light and matter interact, which is itself a function of temperature, pressure. So the way information is encrypted is basically defined by basic quantum calculation. And if you know that, you can invert and retrieve information about your number density profile, your temperature profile, your pressure profile. That's the basics. So I'm going to move forward to just skip a few things to get to a point where at some point in the appendix of the paper, it's basically showing how different part of your line or your molecular feature, top, bottom, wings, record information about the apparent size of the planet, the atmospheric scale height, the number density, and various other properties that relate to your temperature pressure profiles. So information is recorded in various ways throughout different molecular feature. And because they are recorded in different ways, and that's the important bit, because you have different relationships for each of these key parameters, you can break the degeneracy and basically constrain properly these important properties. There's no degeneracies. Right, that's great, but it requires that we actually know the basics of light-matter interaction. And so that's really what is missing. And to make that point, I'm showing here a summary of one of the largest database that we have, which is Hydron. There's different generation of Hydron. And specifically, I'm focusing on broadening parameters, which tells us how a given molecule and its line are broadened dependent on the background gas. So if I have a molecule of CO2 in a background of hydrogen, of helium, of CO2, or something else, the way each of its line are going to be broadened by this collider is very different. And the number that you have next to these tells you how much information we have about it. 3 means we're good. We have enough information to do a pretty good job. 0 means, not so great. And you can see that this is mostly populated by 0 and 1s. So we're really lacking information there. And I highlighted this part of the table simply to showcase CO2 broadened by H2 and make the point that we actually don't know how CO2 is broadened by H2. And so to go back to this molecular feature that I kept on pointing out to you at 4.3 micron, we're looking at this key feature. In fact, the first molecular detection of JWST was that CO2 in a gas giant atmosphere, so a background of hydrogen. And we actually don't know how this CO2 is broadened by hydrogen. So how can we expect to properly infer the properties of that atmosphere if we don't know the basics of how CO2 interact with light in a background of H2? And that is the basis of the opacity challenge. So what we did, so being sensitive to this information content since 2013, the work I wanted to do is to ask ourselves the question, okay, what don't we know about this light matter interaction, and how would it affect the inferences that we could get? So what you see here on the left is a series of synthetic, what we call injection retrieval. So what does it mean? We create a synthetic spectrum with what is considered by the community as the default understanding about light matter interaction. And then we look at the different hypotheses or limitations that are there, and we perturbed our opacity models along different axes that account for these assumptions, these imperfection. And then we analyze the spectrum with these perturbed opacity models to get a sense of how much bias, how much shift we get in our inferences when we do that. Okay. So in colors, you see the posterior probability distribution using different perturbed model. The width of this posterior probability distribution gives you a sense of how well that information, specifically the number density of CO2, can be constrained by JWST, right? And you can see that that obviously doesn't change based on the model that we use to make the inference. The uncertainty from the instrument is the uncertainty of the instrument. So the width of that profile doesn't change. What changed, however, is what is found as ground truth. And you can see it changes by, up to 2 orders of magnitude. It's 2 units or more, well, about 2 units in log 10 space. So it's quite significant. And most importantly, the spread is much larger than the size or the width of this profile, which means the uncertainty stemming from our lack of knowledge of light-matter interaction is significantly larger than the instrument-related uncertainty. Or in other words, while we have improved our technology, we are not anymore in an instrument-limited science regime. We are now in a model-limited regime. The extent to which we know light-matter interaction is preventing us from using the instrument at the highest of its capability. So I won't get further into the details, but long story short, these different colors relates to different perturbations that we looked at, from our understanding of temperature dependence, pressure dependence, broadening parameters, wings behaviors, and all of these things. And what we found ultimately is that most of the limitation relates to our lack of understanding of pressure broadening, which is why I was showing you this plot before. It was a bit of a spoiler. And it revealed that we have an accuracy wall, that despite the fact that the instrument could be constraining these parameters down to maybe 0.001 dex, or at least 0.002 dex, we may have a bottleneck at 0.5 to 1 dex, which means, for example, that the abundance of gases or the temperature in some instances cannot be constrained to better than a factor of 2. So that's, or 3 in this case, 4.5. So that's basically the takeaway message there. So fortunately, since then, yep,
Joey?
question?
Yeah, I mean, doesn't your model assume uniformity composition of the atmosphere with height? And couldn't it change with height as you're measuring these things?
Yeah, that's a great question. So for this injection retrieval, that was the assumption that was made. The intent was to be able to keep the models simplistic enough to be able to highlight the issue associated with the opacity model, because if we complexify it too much, then it's not as easy to explain the limitation that we see. So this is the best case scenario that we're showing here. When you start accounting for higher level of complexity with the planet model, which is that that blob that I was showing before. Sorry about that. Then if you start accounting for higher dimensions in this model, then yeah, things get complicated. Like limitation from this model gets to crosstalk with limitation from this model and so forth. So yeah, it's the bare minimum is what I was referring to here. With our current understanding, in a lot of cases, we have that limitation. Yeah. I think we have another question from Pete. Is that possible? No? Okay. All right, then I'll keep on going. So fortunately, the future is bright simply because since then, we appreciated the fact that solving that problem would take us decades if we were to go straight to labs. And owing to the supercomputer that we have at hand, we realized that ab initio calculation actually was the way to go. And so what we did is we teamed up with colleagues in France and colleagues up at the CFA at Harvard. And we started developing a framework where we can actually compute what's going on in computers. Okay. And so what we did is we estimated for each of these key parameters, what is the precision that we need to have in order to have perturbation in the sigma space. So sigma being here, the uncertainty associated with the instrument precision, that is below 1. So in other words, what is the precision we need to have on our parameters so we get back to this instrument limited regime rather than being in this model driven regime. And typically for broadening coefficient, we need to have a constraint on them within 10%. And just so you know, right now, the uncertainty is more a factor of 2 to 5. So 200 to 500%. And that's why we are way out in the regime that is model limited. And the first paper that we put out actually late last year, earlier this year, showcased we have really only had one measurement for the CO2 H2 system, which is here, and these are the calculations that we made. So we are well within 10%. So the future is bright in the sense that we've created a platform where we can start producing these things. And while initially we thought it would take 6 months of supercomputer time, we've managed to update things, upgrade things, optimize things in such a way that we can just do this kind of work in 2 weeks for a system like CO2 and H2. So we can start producing this for molecules that are not too complicated. And so with that, we should be able to reliably map abundance, temperature, and pressure profile in the GWST era, which is pretty exciting. Now, the counterpart of that relates to our lack of understanding of stars. And I'm going to go really quickly through this just to give you a sense of what is. And if you want more, we can come back to it once we're done with the rest of the content. The basis is that when a planet passes in front of its star, what it is masking, the core that it is masking, is actually not of the exact same emission spectra as the disk of the star. And because we work in relative, meaning that when we do transmission spectroscopy, we look at what's happening on the outside of the transit, and we assume that the transit depth variation relate to a relative change from that. Because the core that is masked is actually not of the same spectrum, we have some contamination from the difference of the spectrum that's blending in. So when we are looking at the transmission spectrum, we also have information about the star. And that was really nicely highlighted by quite a few of the first press release from JWST, where you could read things of that kind. Webb finds water vapor, but from a rocky planet or its star, simply because of stellar contamination and our inability in a lot of cases or our inability to disentangle between the source of these two signals just from the transmission spectrum. And the reason why it's so important, especially as we start moving towards discussion of exohabitats, is that the goal to study the world like TRAPPIST-1 is to get to the 10 ppm precision. And the first spectrum that we got for TRAPPIST-1 with JWST showed variation due to stellar contamination, which is what you see, especially at short wavelength, of the order of 100 to 1,000 ppm. So we have to go 1 to 2 orders of magnitude beyond the challenge of stellar contamination to get to a proper study of planet like TRAPPIST-1. And so over the years, we've developed a series of technique, and I'm actually not going to go through that simply so we can keep time for questions. And you'll have to trust me on the fact that we're on the right way. And if you'd like to know more, I'll give you some feedback. So we can talk about exohabitats. So owing to the fact that we've put together a series of methods in a nice roadmap that I will present in a second, we can be quite optimistic about the fact that there's some great work that is going to come out of the pipeline in the next 2-ish years with regard to exohabitats. And so as we said earlier, at some point in 2015, 2016, we got really lucky and we found this system of 7 Earth-sized planets around TRAPPIST-1. As I said, it was found with a prototype TRAPPIST, which is in Chile, 60 centimeter. So we have these 7 worlds that are around a star, TRAPPIST-1, that is exactly the size of Jupiter. Right? It's in these amazing size regimes. One of the things that I really appreciate talking to my student about is that there's this size regime where the equation of state of hydrogen and helium lead to a constant size for 2 orders of magnitude in mass. And that's really what we're looking at here from Jupiter, well, a bit less than Jupiter, all the way to about 100 times the mass of Jupiter. You have and the first generation of stars, well, not generation, but late time M's that are about the same size. And they are so small that the transit of an Earth in front of it is 100 times deeper than the transit of an Earth in front of the sun, because that star is 10 times smaller. So much easier to study. So of course, it allows for us to study or to hope to search for signs of life, but it also provides us with an incredible opportunity to revisit our understanding of terrestrial planetary system. We have 7 worlds tightly packed next to the star, right? I mean, literally, if you look at what's below down here, it's the size of all of the 7 orbits of TRAPPIST-1 around itself. Okay, so it's a really tightly packed system, 8 billion years old, and it's only stable because it's in this multiple triple resonance chain that we could talk about too, if you'd like. Okay, so obviously it made the news, you know, all that. We initiated in 2016 with Hubble the search for atmospheres. First, easiest to be done is to search for this very puffy hydrogen-dominated atmosphere. We didn't see this big variation, so we could cross off the existence of primordial atmosphere, and we had to wait for JWST to search for this secondary atmosphere. So that's what's been happening. So next steps relates to this roadmap. This roadmap was designed based on the ensemble of studies that we've made over the years and basically help us understand what to do when we find a new terrestrial planet. Get a sense of how to get to a place where we can say, stop using GWST. There is no more work to be done. And there are many reasons for that. Usually, it goes along the line of if you spend X amount of time on it and you still don't see wavelength dependent variation, meaning an atmospheric signal, stop. If you do see one and there's something interesting, put 4 times more time and dig deeper into what could be there. That's the basis of this. So I won't go into further details, but that, if you're interested, can help unpack the whole process. And so one of the things we wanted to prove, and that's what we did on July 9th, 2024, is that one of the methodology we have developed to constrain the effect of stellar contamination work. And that methodology is here, right? If there is another planet in the system for which you have shown that there is no atmosphere, then use that planet to do a back-to-back transit. And that planet will be recording in its transmission spectrum the information about stellar contamination. So you can use that to anchor your correction of stellar contamination and remove that from your other planets. Okay, so that's the basis of this. If you don't have high fidelity stellar model, there is a way to still do some level of correction. And so what we did on July 9th, we got this back-to-back transit of TRAPPIST-1b and C. We knew from emission measurements that there shouldn't be an atmosphere around B. So the intent was to demonstrate that we could do a really good correction for C. Long story short, what you see here in blue and in orange are the transmission of TRAPPIST-1b and TRAPPIST-1c. You can see that they have very similar behavior. And we can show that by using one to correct for the other or vice versa, we can beat the noise down to a level of almost 40 ppm. And that's very fortunate because 40 ppm is enough to reveal the dominant feature. Typically, atmospheric feature for planet like the TRAPPIST-1 planet are between 150 and 200 ppm part per million. So we have demonstrated that we actually indeed have a mean to correct for stellar contamination and start hunting for secondary atmosphere in the TRAPPIST-1 system. And that's what's going on right now. So there's a few programs aiming at revealing or at least assessing the presence of atmosphere around planet like this one. Great. So that's about finding planetary atmosphere. What I wanted to talk to you about is a paradigm to help us assess for the presence of liquid water or life. And I'm sure if we think of life, you're aware of the old paradigm, at least, which relates to if there is life as we know it, there should be a large amount of oxygen. What you see here is the partial pressure of oxygen versus time, going back in time. And as large-scale biomass emerged, oxygen got to very high level, like level so high that if we didn't have large biomass, oxygen will be relatively quickly removed, at least on geological timescale. One fun fact that's worth highlighting, and I don't know if people necessarily know that in the audience, is that if oxygen was not at this level of pressure, partial pressure, we wouldn't be able to get flames, make fire, get engine. So the level of oxygen that we find in Earth's atmosphere, specifically above 18% is key, is actually allowing for industry as we know it, engine and so forth. So that in and of itself is kind of interesting to understand the type of complex organism that may or may not evolve on planets based on the access to this type of accessible energy, such as O2 in high quantity. Now, the challenge with oxygen is that it's difficult to explain. as a biosignature. There's a lot of false positive. And on top of that, as you can see on the spectrum, where you see here Earth seen as an exoplanet, oxygen is challenging to find. You don't see oxygen marked on this spectrum, right? Simply because oxygen is a few tiny lines here and there. So it's not only difficult to interpret because it could be produced by different geological processes in some environment, it is also difficult to detect. So oxygen is actually not the obvious choice. And so the new paradigm that we put forth is based on this plot where you see here the pie charts for the constituent of the atmosphere of Venus, Earth, and Mars next to each other. And you can see very clearly that CO2 is what dominates Venus atmosphere, Mars atmosphere, but it clearly isn't there for Earth. And so how do we explain this difference in composition? Okay, that's where I'm going to make this a tiny bit interactive. Can I have a feedback on this? How do we explain this difference in composition? Anyone?
Isn't CO2 trapped in the oceans and they become a huge store, essentially?
Exactly. Yeah, it's as simple as that. Like the CO2 is just captured by water cycles. Okay. So the basis of I think one of the paper you wanted me to discuss relate to connecting the search for strong water cycle to something that is missing. And usually when we think of and just to close the loop maybe on the argument here, we we do know that Venus actually was also habitable at some point, right? So what you see here is bar charts that shows the volcanic activity for different worlds, so Earth, Venus, and Mars versus the liquid water at the surface. And typically you lose liquid water first, and then liquid water and actually carbon dioxide are both helping with plate tectonics. And so volcanic activity starts dropping when you lose the carbon dioxide because it goes back into the atmosphere, and that's a really good lubricant for the plates as well as the water. So long story short, all of that is connected. And so what we proposed is instead of going around and trying to look for things that are added to the system, meaning if you have oceans, then you can look for the ocean glint. If you have a biosignature, you can look for the added signal of oxygen or CFCs if it's a techno signature that you're looking for, and so forth. And we said, well, instead of looking for these things added, why don't we look for things that could be removed? And the first thing that came to mind is CO2. Like we do know that terrestrial world are most likely to form secondary atmosphere that are rich in CO2, such as Venus atmosphere, Mars atmosphere. If we were to find a system where indeed most of these terrestrial world have CO2 as the primordial or the primary component, but one is strongly depleted, clearly something of large scale is happening to remove all of this mass from the atmosphere. And that's either liquid water, strong cycle, and in fact, even plate tectonics need to be involved for some level of depletion. And or there's strong biomass that is able to capture that carbon and use that carbon as a backbone for its organism. Okay. So why CO2? Well, by now, I'm sure you've gotten the point that CO2 is really nice molecular pH at 4.3 microns, so it's easily detectable. In fact, that's usually what we're targeting to search for the presence of an atmosphere, deviation from a flat line around 4.2 micron, which will be a sign of an atmosphere. And then if you fast forward and really invest about 100 transits of JWST time on the system, you can disentangle between a depletion of CO2 without ozone and a depletion of CO2 with ozone. Why? Because oxygen that I was talking about is a waste product of a biomass consuming CO2, rejecting oxygen. And then if there is enough of that oxygen that builds up, it gets degraded in what would be a stratosphere and would most likely produce ozone. And so ozone will be easily detectable. And so if you were to find a CO2 depletion for one of these worlds in the next 3 to 5 years, as well as a molecular feature of ozone right next to it, which is convenient, then you would have pretty good chances to say that you have found a large-scale biomass in the atmosphere of another world. Fabulous. So I know I'm getting at the time, which is perfect, because there's one last thing that I wanted to talk to you about, which relate to the other half of this weird title, defending life here on Earth. Like, what does that relate to? You got the point that it relates to asteroid, but how do we connect the two, right? How do we talk about planetary defense with GWST? Well, one of the things that we started to do in 2020 is to leverage the large amount of data that we've gathered, hundreds of terabytes with speculoos on sky, to search for other things in our field of view, planets around other stars than our target, but also asteroid passing by. It's easy to find asteroids when they are visible on separate exposure, but when they are too faint to be detected on a individual exposure, there is something called a technique called synthetic tracking that involves shifting and then stacking exposure in different direction and seeing if something pops up, just like what you can see here on the little image, right? There's a little asteroid that pops up, and what you see are other stars trailing because you've shift and stack all of the image in that direction, and that shines through the noise. Okay. And so we use our own proprietary data to develop that framework. That worked out great. We applied that to telescope in Antarctica, ASTEP, and really what we were excited about was developing that or deploying that on JRC data. And this is what we put out last December 2025. What you can see is application of that to the field of TRAPPIST-1, where we found an ensemble of main belt asteroid. So what is that about and how that came together? And why is it data from TRAPPIST-1? Well, let me explain. On the roadmap that I showed you before, one of the things that can be done is look at the occultation of terrestrial planets to see if they have a temperature on their day side that is significantly cooler than what you would expect if they didn't have an atmosphere. If they have an atmosphere, if they don't have an atmosphere, their day side, they are tidally locked, is quite hot and their night side is quite cold. If they have an atmosphere, you're going to have something, the atmosphere, that is able to bring the heat from the day side to the night side and redistribute that heat. Okay, so a temperature anomaly could be a sign of an atmosphere. So one of the ways to search for atmosphere around planets like the TRAPPIST-1 is to do observation in the 10 to 15 micron band. So places where a terrestrial world, habitable world, is bright. Now, the universe is 3D, so when we observe them where they are bright, we also get to be quite sensitive to things that are bright in our own solar system when they are in the temperate regime, meaning anything between Earth and about 5 to 10 AU. That's convenient. And that's what you can see on this plot. What you see on this plot is the normalized radiation density for objects between 1.5 and 3.5 AU. And you can see that they peak really nicely, or the thermal emission peak really nicely in that wavelength range that we are using for a TRAPPIST-1 observation. Perfect. And these objects are significantly less bright in the visible. So we get to see things that we can't otherwise with Earth-based facility because in the visible they are way too fit. And that's what this plot shows here. We get to be sensitive. So in dashed line is what you can do with, really powerful facility from the ground down to Vmag of about 27. And anything under down to the blue curve is what we easily get access to with JWST. So this whole part of the parameter space is uniquely accessible to JWST. So what we did is we just turned on the lights and looked in the infrared, and we found a huge amount of small asteroid. To give you a sense of our sensitivity shift, until recently, let me just look at this. We were able to detect objects in the main belt down to size of, say, about a kilometer. And now with our technique, we got down to 10 meter in size, right? So we got access to a completely different part of the MBA population. It was in and of itself exciting. But most importantly, the number of these objects really changed the game, right? Based on our understanding of size frequency distribution, I'm going to skip that, we were expecting of the order of 8 known objects in our field of view over the observation that we were making. So all of that is bonus science, right? So it was just bonus science. We're expecting 8 known objects and of the order of 30 additional objects down to 10 meter in size. But we find 138, which translates, and this is what you see here, in an uptake of the size frequency distribution. There were way more small objects than we were expecting based on the projection from the known size frequency distribution down to 1 kilometer in size. And that uptake means that we are probing the collision driven or collision cascade part of the population, which is exciting. And that transition between the two regime is right at 100 meter, which is what was expecting from an understanding of interior property and spin of these objects. So why is that interesting? Well, first, it provides us with a new understanding of this part of the main belt, and that part of the main belt is important because these objects can more easily move to the near-Earth object population. And talking about near-Earth object population, we are sensitive to decameter objects that are near-Earth objects, but only when they pass close to Earth. And now, in that study, we showed that we could do that with JWST all the way out to the main belt if necessary, which means for planetary defense that, there's a lot of cool things that we could do. And in fact, I made sure to end the paper by stating that the capability of JWST to observe decameter object all the way out to the main belt while deriving tighter sizes, because we're not bothered by the albedo flux size degeneracy that we do have to face in the visible, really provide unique capability for the study of future impactor. We put this out on Nature's website, and literally 2 weeks later, the potential impactor 2024 YR4 come online. Makes the news. And then obviously, we got to point JWST to the objects, use that technique and derive its size. And we now know that that object, which is not going to impact the Earth, since then the orbit has been refined, but at least we got a full proof of concept of application, is about 60 plus minus 7 meter in size. So that gives you a sense of how we can leverage various techniques to make sense of reality and help not just, search for life elsewhere, but also defending it right here on Earth. And I'm going to leave it at that and take any question you may have. Thank you.
Arthur, I have a question about the constraints that you were talking about, in looking at spectrographic data and how you're using it. I know that some of the probes that we've sent out pretty far, even all the way out to Saturn and beyond, have spectrographs attached to them. Would it be useful to park one, say around 8, 9 astronomical units out, and just point it back toward the sun and use what we know about the planets that we have a lot of data on, and see how that would provide you with constraints on a lot of these confounding things that can affect the behavior of spectrographic data?
Yeah, it's a great question. So that's been done. This is like there are a bunch of paper that says Earth as an exoplanet, Titan as an exoplanet. So people have done these types of exercises. Yeah, and we face the same issue. Like for example, Titan is a molecular feature that can be interpreted in so many ways, and these ways are dependent on our understanding and the generations of opacity model that we use. So these types of efforts are made, and they are very informative, and they are as relevant as studying brown dwarf, because brown dwarf have really high signal-to-noise ratio, and the information that we can get about them is comparable. So these two are avenues to help us push the boundaries of what will have to be done in order to do good exoplanetary science in the next 10 years or so. Yeah, so these are good approaches.
Like to get time on the JWST, is that hard to do?
Uh, I, it's I think honestly it's okay. What has been challenging over the years is that the number of proposal has spiked. And I don't know if it's because people are more and more creative or because people are starting to use, ChatGPT and AI tools to put out a large number of proposals. So we are getting to a point where it's easy to get drowned in the noise. And a lot of really good proposals are just um, I think it's challenging on the reviewers too. It's a lot of proposal to go through, and sometimes a lot of really good proposal. And I'm gonna add one layer to my comment, which is due to the large number of proposal, some agencies have half the number of pages that you have to argue for your science, which means the a lot is left to the reviewers. A lot more is left to the reviewers to assess, is this really some strong science, or it's just a fancy pitch that may not lead to solid science on the other end. So it's yeah, it's we're learning to navigate a larger community and tools to produce compelling narrative that are not always as sound as they may sound. Yep.
Question, I know most of the data you have for the spectra are taken in the visible and infrared. Would you benefit from millimeter or microwave? And do you have that available, or what would it take to get that, if it makes sense to have that available?
Yeah. So high energy definitely is worth it. Lower energy, there are some instances where um, magnetic interactions are looked for. So that is informative. And there's at least one instance where, and that's not recorded, right? So I can easily say whatever I want here. Perfect. Though there is at least there is at least one instance where we do have a star with a spot, and it does seem like there's an interaction between the star and its spot. So in that case, we could really look for a magnetic interaction and potentially periodic reconnection. So that would be of interest for that system. For the rest, no. I think only if you move to study of disks, will those wavelengths be of interest to you? In other instances, the information or the signal to noise ratio is not sufficient.
Thank you.
Of course.
Billy, can I ask you a sort of unrelated question, just because I noticed you published with Sarah Seeger?
Uh-huh.
Okay. Your thoughts or comments about this question of phosphine in the upper atmosphere of Venus and its potential as a biosignature, or is it, it was refuted, then it was confirmed, it was refuted, and you're an
Yeah.
expert in biosignatures. I'm just curious.
Yeah, so for context, Sarah was my PhD advisor, and we've known each other for a long time. So the phosphine situation, I think, is compelling and interesting because it really forces people to think outside the box with regard to chemistry. And I've been somewhat involved with the work that's been done by the chemists around that, and it's fascinating to understand how they view chemistry, right? And I didn't mention that, but I started a class that's called Our Space Odyssey, where we think about these concepts, and life as we know it is just a complex form of chemistry, and chemistry is just very efficient basics of physics happening in some close element. So long story short, what they're doing is they're now appreciating the fact that if you were to think of a multi-dimensional parameter space, what we see as an island of habitability for us is quite detached from what will be an island of habitability for a life form like the one that might be there on Venus, simply because the solvent will be actually sulfuric acid. And believe it or not, they've done a lot of experiment now, and more are finding key building blocks that are highly stable in sulfuric acid, while we were thinking they wouldn't at all be stable. So it seems like there's more and more compelling evidence that not only phosphine is there, but there could be some complex chemistry that would be stable with sulfuric acid as a solvent, which is really cool to think about, because if we go back to, and I know it's dreaming, right? But at least it gets us excited and it gets us thinking about things beyond the usual stuff. And if I go back to this slide, right, let's keep in mind that Venus was most likely quite habitable for a long period of time. So if a complex biomass, just like there is on Earth, were to evolve. And at some point, over hundreds of millions of years, water moves and the solvent that is accessible is more sulfuric acid. These are timescale over which a biomass could evolve, and it's not so crazy to think that they could be the leftover of a very complex biomass whose ancestor have ended up in the clouds of Venus. Right? There is life quite high up in the atmosphere of Earth. So um, I think it's definitely worth going and checking it out. And if we step back, there is no reason to commit to Mars without committing to Venus, considering that they are both near Earth. And, looking at Mars, conditions are not necessarily more hospitable, right? There's no real atmosphere there, so why not?
Thank you.
Mhm.
Well, thank you. I think if there's no more questions, Julian, thank you so much for your talk.
My pleasure. All right. Well, you know where to find me. So if you have any follow-up questions or so, please feel free to reach out.
Thank you.
Bye-bye.
Well, the game certainly gave me a think about. Anyway, we're about to break for summer, and that's always good news to us. So I like to get out under the stars, but there's a lot of events coming up. Don has a full schedule this year. In fact, the fullest schedule I think that I've ever seen in terms of events coming up. So just because we're not having indoor meetings, don't think that we're not going to be busy. Especially if we're hiring anybody that even has a pair of binoculars, come on out. We need you there. All right. So everybody go, have a great summer, and we'll look forward to seeing you out under the stars.
Hi, John.
Good evening. Got here a little late tonight, sorry.
How you doing? Hi, Pete. You're muted. I muted you, Pete.
Take care, everybody.
All right, Sue. See ya. Kathy's waving to you, John.
Oh, I can't see her. Where is she? Is she there? Why isn't she in Florida?
Waving at the screen like you can see me.
Hey, are you back?
But yeah, finally there. We got back last weekend.
Okay, so you're up for the summer now.
Yeah,
Okay.
hope to see you this summer. All right. My meter's running out.
Okay, and we know what the parking fees are like, or parking tickets are like in Westchester, so.
Can't hear you.
The parking tickets are pretty expensive, as I recall.
Oh, yeah, I know. Yeah, I've been a recipient.
Pretty good crowd tonight.
Yeah, yeah. How many people were online?
7. We had like 26, 27 between the two. So yeah. Hey, down there, you weren't on earlier, but that's Krishna and Sadhvi Prasad. So Sadhvi, they're gonna send you her essay because she won 3rd place in the Astronomical League Horkheimer Award, journalism. So we'll send it to you so you can put it in the newsletter, okay?
Yeah, that sounds great. Yeah, and then we'll get to see the write-up in the Observer too.
So then she'll get a plaque, and we'll get a picture of her with a plaque too.
Great.
All right, I'm gonna shut it down.